There's a lot to talk about astrovisualization and so forth. And I'm telling you, I was so absolutely, totally flabbergasted by that visit with you to the site and everything, and it's amazing. And sorry we couldn't get it going. And welcome very much to conversation. Of great pleasure to welcome to the program Carter Emmart, and his title is the Director of Astrovisualization for the Rose Center
For Earth and Space.
For Earth and Space at the the Museum of Natural History here in New York City, and he is on the cutting edge of visual display as it relates to the whole of the human experience. I would say we had an example of that last week, and we're going to be talking about that here. We were going to demonstrate some of the incredible graphics that they have at their behest there and so forth, and that he's a master of manipulating. But due to our problem here, my problem here, we weren't able to get it connected up, but we're going to talk about it in general. And Carter, welcome very, very much to conversation. Sorry we couldn't get our machines working right.
Thank you. It's a pleasure.
I wonder if you could, Carter, what do we do? We got a whole hour, okay? And what if you could share your own background, please? We were born and raised, a little you're educated, and then we're going to want to talk about this whole concept of visualization, which is something I think we're all due to talk about in a major new dimension in the time ahead. But your own background, if you would, please.
I was born in New York City and raised in New Jersey. I was born in 1961, which is an auspicious year for, of course, for space.
Yeah.
Just a couple weeks after I was born, I was born 5 days before Kennedy was inaugurated, and so 2 weeks after I was born in mid-January of '61, the first American astronaut flew, Ham the chimpanzee.
Oh, that's right. That's right.
And Ham, the chimpanzee, preceded, of course, Alan Shepard and then the Mercury astronauts. But Yuri Gagarin flew on April 12th of 1961.
And the first Sputnik set it off, right? In 57 was
in 1957,
the Russians had put up Sputnik?
In October of 57, the first satellite was launched by the Soviet Union.
Yeah.
And then
threw this country into a tizzy.
Yes, and it formed NASA. And then also the original 7 astronauts were recruited to really be the first person in space. And the Russians trumped us, or the Soviet Union trumped us with Yuri Gagarin's flight.
That's right.
Just prior to a month before Alan Shepard flew. And
the
they also
space race was on. Huh?
That's right. And they also that first shot of Yuri Gagarin was an orbital flight, and our first 2 Mercury ventures into space were 15-minute suborbital, parabolic, just ballistic flights out into the ocean. And then John Glenn, of course, was the first to actually get us going. But I grew up in that period. I grew up in a family of artists, really. My father was a commercial artist working for Ogilvy and Mather here in New York.
Big PR firm,
Yes, and so
he was on the design side, the artistic side.
My dad was a sketch artist for all the storyboards and so forth for doing commercial presentations.
Great training for you, I would think, because you're dealing with templates all the time and storyboarding in a sense, I guess.
My father had an intense interest in history, and so we had a wall of National Geographics going back to the second issue. Our first issue that my grandfather got was lost in the mail.
Right.
So,
so it was intellectually stimulating.
It was.
When you were a kid, you were stimulated by the intellectual curiosity of the family.
Right? I think I gravitated a lot toward the visual because my father's profession. My grandfather was an architect. There's a family history going back in art, sort of a Dutch background. But one of my first memories was going to the American Museum of Natural History.
That American Museum of Natural History is a danger to me because I sometimes just can't get out of there. It's so damn interesting.
It is, and it was, of course, it's inspirational to to so many. I mean, every day when you have to fight upstream just to get to your office past a sea of sixth graders and so forth, I'm constantly reminded who my bosses are, and my bosses are all about 3 feet tall.
Oh, I see.
So,
I see.
yeah,
Yeah, that's right. The educational implications are fantastic of the display and the what do you call those where you have beasts and so on?
We have mythic creatures.
No, not that so much, but they have these exhibits where you have a mastodon or something, and they call that thing a darium or something.
Oh, they're dioramas.
Dioramas, that's what it is. Yeah.
And our tradition of doing diorama art is perhaps reaches its peak in the experience when you walk into the Akeley Hall and you're confronted by a herd of elephants.
Yes.
And it's quite amazing to. Walk through the museum after hours when you're the only person in the Akeley Hall with the herd of elephants and these beautiful dioramas.
Yeah, they really are works of art. I mean, they're gorgeous.
They are.
And they're precursors to a lot of what's going on in the digital world now, I would think.
Absolutely. In fact, I'm glad you bring that up because really the task at the Rose Center when we decided in rebuilding the Hayden Planetarium, I joined the crew when the project had been initiated and started.
When would that have been?
This is we basically tore down the old Hayden Planetarium in 1996, 97,
about 7 years, 10 years ago.
And then it reopened in 2000. I had the great pleasure and honor to join the team in 1998, so I'm going on about 9 years of employment there. But the concept was very interesting. The planetarium was developed by the Zeiss company in Germany in the 1920s, and the idea was to recreate, if you will, a diorama, experience really of the night sky. A tremendously
and they
inspiring.
Used that term was used in those in
the
that
planetarium.
World of design then? Yeah,
yes,
for a planetarium.
So the idea was to project the night sky, the stars and the planets and the moon and sun, and you recreate the diurnal motion of the sky.
Diurnal being daily.
That means a daily motion where you see the stars, rising and setting, and then the sun comes up, of course, every morning and sets.
And they were using what best technology they had in order to help present these images and so forth.
In the early 20th century, you had basically optical mechanical device, and it was a sensation.
Yes.
And the Hayden Planetarium opened in 1935.
It did. That's the year I was born.
Okay.
That's the year Social Security began too. Whole lot of shaking going on in 35, huh? Yeah.
And it was 5 years before, of course, the World Exhibition.
That's true.
The World's Fair of 39, 4 years.
Yeah.
Yes, and so 39, 1940, and of course, just predating World War II.
March on Poland.
The concept for updating the planetarium was an interesting concept. When I heard about it, I had my skepticism that it could even be done. But technologically, was that if you could repurpose the dome with a digital projection, and in fact, we had already decided, or the museum had decided, to buy the latest, greatest Zeiss projector, which really is a wonderful device. That is the traditional optical mechanical way of projecting the stars. But the computer control had the potential to show not only just the stars where they are, like the optical mechanical, what we see of the sky, but really present that it's a three-dimensional data set. So we know the distances to stars, not only just where they are in the sky.
I know.
And so once this information is input to the computer, one can leave the position where we are locked, essentially. We are, of course, all the stars that we see, we are part of a galaxy, which is a much larger expanse than we can actually see with our naked eye. The Milky Way that we see when we leave New York City and get out to a beautiful sky, we see that band of milky light. And that is, it's been resolved over the centuries that really is a much greater place of our home, of where the sun and the regional stars that we see are actually just a tiny subset of this larger mother galaxy, if you will, which we call the Milky Way in honor of the Milky Way band that we see across the sky. And so the idea is that we would then be able to move out into this three-dimensional
it's so exciting.
expanse.
Yeah, right, three-dimensionally.
Yes.
Yeah, right.
And
okay.
that process and that profession is something called data visualization. So we are visualizing the data so that we have this 3D data.
So you're a visualizationer.
I am
it's a mouthful, yeah.
I'm a data visualizer, or I direct the data being put into visual form, specifically for the Hayden Planetarium, which is now part of the Rose Center for Earth and Space at the American Museum.
Okay, I wonder, let's back up just a little bit, because we're talking about a major institution here in New York City or in the world, and that being the Natural History Museum. The Hayden Planetarium is, as you say, the history, natural history. One thinks of the evolution of Earth and the creatures and the forms and so forth on the Earth, but you're talking bringing the astro. That's something. When was the astro part of it? Why don't you just give us a little bit of a quick rundown on the institution of the natural history itself, and then when did the space aspect, the Hayden Planetarium, or this astro addition to the natural world, which is part of the universe out beyond the Earth. But do you understand what I'm saying? Just a little thumbnail history of the thing. That's where Margaret Mead used to hold.
Yes, the grand institution of the American Museum of Natural History goes back to 1869. 1869. And Ulysses S. Grant helped, I think, dig up the first shovel of dirt, if I remember this correctly. However, the astronomical component was actually there from the beginning.
Oh, it was? Okay,
yes.
That's good.
And so our meteorite collection, and in fact, there's a great picture of the Willamette meteorite arriving from Oregon, where it was extracted and then brought by ship to New York. Willamette meteorite.
But it's called Willamette after a geographical location?
Willamette, yes.
Illinois?
No, it's not Willamette or
Willamette,
Illinois. It's from Oregon.
Oh, okay.
But there are great pictures of it actually coming to the early museum by mule, by a pack of mules, and this meteorite being towed to the museum. So the astronomical realm of the sort of natural world, or our world within the astronomical, was really there from the beginning. And these artifacts of something from space were incorporated.
Part of the natural world,
yes,
as you think of it. So the astro is a different thing. And then was there, before that, was there something at the Smithsonian or something before that, or something in Europe where they have a museum in Chicago, a natural history museum. I remember visiting that when I was a kid. These natural history museums, is that like in Europe museum, or go back to Alexandria, or what? Well, you know, the attention to the natural world that is the hallmark of our Natural History Museum here in New York.
Well, it's interesting, these collections, when Europe began to explore the exploration of beyond Europe and going out into the world, this tradition a few hundred years ago of curiosity cabinets.
Curiosity cabinets.
Yes.
That's a cabinet with curiosities in it.
That rich barons and so forth would put together collections from the natural world of shells and things like this, and this interest in science, or this categorization of information, really began. And this led to.
Are you going Renaissance time or
no? Later than Renaissance time, but I mean, collections have probably, I know, for star maps and collections of information goes back to antiquity and goes back into the ancient world,
I guess
of course.
It does, and taxonomy and all of the kind of things. And I mean, it's so interesting, the world. It is so interesting, and that anything exists is so interesting, but that we have a way of taking notice of it all is really important. It must be exciting to be part of that realm.
It is.
Particularly if you come from a curiosity thing where you have pictures of National Geographic all over the walls that you grew up with, right?
Right. Well,
must have been like a dream come true.
Well, it certainly is. I have a picture that my father took of me after when I was 8 years old, and I'd come home. My mom had taken me to the museum, and when I came home, I wanted to have the dinosaurs, of course, but I made clay models of the dinosaurs.
You did?
So my father took a picture of that. I have that hanging outside my door
you
to
still
constantly.
Have the clay model?
No, but I have a picture.
That would have been great.
And it reminds me.
Oh, the picture.
It reminds me from which I'm coming from,
Yeah,
which is the inspiration of this museum in my psyche.
Yeah.
I started taking classes at the planetarium, the old Hayden Planetarium, when I was 10 years old.
You did, really?
Yeah.
Okay, so you were there. That's the old stomping ground.
And our director, Neil Tyson, as well, was a child there.
Was he really? He's the director of the museum overall now, right?
No,
of the
Neil,
Rose Center.
Neil is the Fred Rose Chair, director of the Hayden Planetarium.
Yeah, he's very articulate. He's in the public view a great deal now, and talking about astrophysics and sort of taking up where Carl Sagan used to be in a way.
Yes, and also an advisor to the president's councils and to the government, federal government, on the future of what we should be doing in space.
You're on the very cutting edge, it seems to me, having been to your institute, your Rose Center, and it was really grand seeing you and so forth with some people here, public access. We're interested in public outreach of what's going on in terms of intellectual expansion and so forth. And it seems to me, I know you got to set me straight, okay? But it seems to me you're involved in the colleagues with you. We met a couple of young men from Sweden, and there's some people who are in this field of visualization, which taps into not only the astro world, and we're getting now to where we have such a vast ability to understand and take the measure of the whole universe. I said to your colleague there that I was talking to Michio Kaku, the physicist, and they're going to have a telescope array that's going to be operative in 2011, that they're going to take a photograph, a picture, an image of the shock wave of the Big Bang 13.7 billion years ago, which began this universe. There may be parallel universes with wormholes and whatnot, but it's so interesting. Within a nanosecond of that event, 13.7 billion years ago, that really is a mark of the ability of this Homo sapien consciousness to take the measure of the universe in a new kind of a new and interesting and qualitatively new way than has been our capability. And it must be exciting to be right on the cutting edge of all that, if you understand what I'm saying.
Yes. Being able to understand a lot of this and contextualize a lot of this new information that's come to us from the astronomical realm is really what our day-to-day job is in the production of our shows and so forth.
What a wonderful thing to be doing on a day-to-day basis. You must wake up just joyful every morning.
Well,
right? Every morning, almost every
I do.
morning. You do?
Sometimes I'm staying there all night at the facility just because during the day we operate the theater for our audiences, but to actually do a lot of this work, sometimes we have to stay late in the dome. But there's something almost, it's a very interesting feeling to go into the dome and actually call up, for either a public presentation or just even in working with it, these data sets. And not just, we produce these movies, and if you come to the museum, you'll see our productions. Our latest one is Cosmic Collisions.
It's staggering.
It took 2.5 years to really sort of put the whole thing together, about 18 months of real prime production cycle. Robert Redford narrated it beautifully, so our big productions have a basis in or visualizing process. Astrophysics is all about process, so understanding the process of the universe. But the basis of being able to make these productions is this atlas of the universe, which is the knowledge and data set, if you will, from the Earth out into the solar system where the planets are and so forth, and then beyond that actually out into the stellar realm of the stars that we can measure, then beyond the galaxy, the galaxies that surround us, and that they go out and go all the way back effectively to a limit or a horizon on that which we can see. You have to remember that light travels at a very rapid pace. It travels at 186,000 miles per second.
That's kind of fast.
It's quite fast. However, now think about this for a second. where do you see such distances? You see it with the Earth-Moon. The Moon is 240,000 miles away.
Okay.
So that means that a light beam from the Moon to the Earth has a delay of about a second and a half.
I see. The Sun's what, 93, 97 million?
The Sun is 93 million miles away. And so light travels from the Sun, takes about 8.5 minutes to get from the Sun to the Earth.
Right, right.
And in fact, the speed of light was detected by looking at the moons of Jupiter.
Really?
The moons of Jupiter that were discovered by Galileo provide almost like a clock, if you will.
Yeah.
And so you can see very accurately where these moons are supposed to be. But then we noticed that that clockwork got out of kilter depending on the distance of Jupiter to us.
That is, he noticed.
Well, not Galileo.
Not Galileo. It was after him.
Later scientists noticed.
But he was able to see things with telescopes that had been developed, which was another technological development that is continuing.
Absolutely. Yeah. It was about 400 years ago. We're coming up on the anniversary. In fact, there's big anniversary planned in the astronomical realms around this. But in 1609...
He's a biggie in your in your pantheon of the biggies.
Yes, Galileo did not, he did not actually invent the telescope. He was the first to actually train it to the sky and noticed and recorded that the moon, the edge, this shadow edge of the moon, we call it terminator, between night and day, was not smooth, that it was in fact quite craggy, and Galileo dutifully and very beautifully depicted, and he was skilled in recording, as a naturalist does, sort of go out in the field and record in those days just by pencil or watercolor what the edge of the moon looked like, the craters of the moon.
Yeah, that's right. Yeah.
And was able to see the moons of Jupiter, which were pivotal in the notion that we were not the center of the entire universe.
Yeah, but now that was a really heavy-duty thing that laid upon the people of that time. The Catholic Church only let him off the hook about 10 years ago for telling us that we live in a heliocentric world, if I understand.
Right. Well, in the
because that really upset people's sense of identity.
Absolutely.
Hieronymus Bosch,
yes.
paintings writ large. I mean, really shook up people's consciousness. Yeah.
That's right. And you have in the 16th century, you have in the mid 16th century, you had essentially Copernicus doing his
another
work.
Troublemaker.
Yeah. Well, Copernicus was able to put down the notion and simplify the motion of the planets as seen by this hypothesis that the sun was the center.
Yeah.
Aristarchus back in ancient Greece and Alexandria, Egypt, had posited that, but
Ptolemy thought we were the center of the Earth.
Ptolemy was to create the most elaborate mathematical description with the Earth being the center. Yes,
with elliptical pathways and so forth.
Yeah,
and
epicycles.
They would have epicycles,
Yes.
and they would create all kinds of things in order to justify that thing.
That's
and then
right.
it finally came to be.
And
people's identity were wrapped up in that idea.
But you have De Revolutionibus, which is the book that Copernicus brought out really on his deathbed when it was published. 1543, I believe, but he posited that the sun was the center. It simplified the explanations, although it wasn't perfect.
Yeah.
Copernicus still had circles. Essentially, the Earth would travel in a circular orbit around the sun. It almost is a circle.
Elliptical pathways, aren't they?
But the elliptical pathways was a tremendous innovation that was conceived by Kepler.
Yeah.
And Kepler working off the Tycho Brahe's observations, which were the best in the world. And so that was at the end of the 16th century.
Right.
A century which is a tremendous century, which began really just after the discovery of the New World by Columbus and so forth. You had setting sail in 1519. You had Magellan.
Magellan sailed all around the world.
That's right. Setting off from Spain. He was, of course, Portuguese, but he went to the King of Spain and was supported to travel around the world, or actually go searching for a strait through the New World to get basically to finish what Columbus had attempted, which was to get to the Indies, really by sailing west.
Yeah.
And I think what's important about Magellan is that while we knew the world was round from ancient Greece, and Aristotle knew the world was round, and with several very good arguments, that to actually do that travel all the way around was extraordinary. It took 3 years. They set off with about 260 men. One of the ships turned tail in the Straits of Magellan and made it back with 60 men on board. But out of the 260 men that left, and then the 60 who came back, you had 200 men that really were still out there, and only 19 returned.
Oh, we darn.
And
really,
3 years later, in one of the boats, badly damaged, the crew was starving, and so forth. But this ushered in this century where Copernicus then sort of kicked us off the center of the universe, and you finish that century with Kepler.
Yeah.
And Kepler was a contemporary of Galileo. And if I've got the story correct,
well, it sounds
Kepler,
like you've done your homework. It does sound like that's your bailiwick.
Well, Kepler actually asked Galileo for a telescope, and Galileo never sent him one.
Oh, really? Yeah.
But
well, I know among the many things that you've shown me and so forth, and we're just wanting to we got to get up there, because the trouble is everything's too damned interesting. You know, we could talk for 1,000 years on the 5th century.
That's true.
But the thing is that you're in this astrovisualization thing, and one of the things you showed me, you sent me some photographs, which I thank you, after we helped see Reed Stowe off on his 1,000-day venture. And where a lot of people who are interested in things, adventure and so forth, are tracking Reed and Sonia on their venture into the world. They're going to sail for 1,000 days on a 70-foot gaff-rigged schooner that he built with his own hands lovingly, and we wish him all the best. And you're, among other things, kind of tracking Stowe, right?
Yes.
And that brought us together. And you showed me a thing you had about the tracking from the diary of Magellan, the trip, and the things that could be done in terms of visualization, the educational potential of which is staggering.
Here's what I'm interested in Reed's journey so much, other than he's a close personal friend of mine. And I met him at a Mars conference that I was an organizer for when I was in college, and Reed came in 1987 to Boulder, Colorado, where we had this meeting about Mars, and this guy shows up. He's an artist. He had built this boat. He's really a modern-day explorer.
Yeah, absolutely.
And
he may become seen as one of the great explorers. The Explorers Club said, if he pulls it off, he's going to be going the record books.
Well,
and he's out there now, and we should all wish him well. And keep track of him at 1,000 days at sea. What's this?
It's 1,000 days, so 1000days.net.
Right. Then you can track him. Then you're helping to track him. But go ahead. But
it was interesting. Why did I meet him landlocked in the middle of the country in a conference about Mars, of all things? Was that Reed came at this whole idea from the standpoint of interplanetary flight. And a Mars mission would have an average duration, chemical propulsion techniques, of roughly 1,000 days.
Right. Okay.
So he has called this for 20 years now that I've known him. He's called it the Mars Ocean Odyssey.
Right.
And I was overjoyed to see him finally depart.
April 23rd. Mark it well, everyone. From Hoboken, Pier 14.
April.
They sailed off.
April 21st, I believe.
Was it 21st?
Okay, and it was a beautiful day.
Beautiful day.
And we were all there. I jumped on a chase boat, and we went all the way down to the Verrazano with him.
Took him all right past the Verrazano.
But
like we're at Palos saying goodbye to Columbus.
Right.
Yeah.
But with Reed, what we can do is he and Sonia will be out without coming into any port.
And no resupply.
No resupply for 3 years.
It's like a biosphere on the sea.
Yes, and they've already run into another ship.
Yeah, that's
which,
I took one of those big cargo container things. Or
yes, and Reed had told me one of the largest dangers out in the open sea is actually running into another ship, which I thought was absurd. But,
yeah.
but indeed, they've had a problem. The bowsprit was essentially busted off. And
but they're okay, I'm happy to report.
Yes, they're
There's
okay.
There's a daily posting on that site.
Yes.
And it's coming through a Iridium telephone that you and Paul Slackus and others helped put together. So he's got this sort of contact
others had helped
with
put this together. I've known Reed for all these years, and this suddenly got interesting from a standpoint of what we might be able to do in the planetarium.
Yes.
Is that when you look at the future for human travel to the planets, you are looking at these long duration missions, and so Reed does provide this sort of analog. But also, you would still be in communications with them. The one thing that Reed's journey does not have is a time delay, which you would have actually in talking to a crew on their way to another planet. And but nevertheless, Reed and Sonia sailing out, we plot their GPS on the Earth globe. Now, I should also describe that we have this data set that you fly out into the universe, and you're suspended in this sort of three-dimensional, very compelling three-dimensional experience.
Staggeringly beautiful.
And the way this works is that the dome is what we call an immersive display.
That's one of the largest visual display screens in the world. Those domes.
It is. There are domes that are larger. However, for interactive control, which we do in a program that we call the Virtual Universe. We do that every first Tuesday of the month between 6:30 and 7:30. It's a public program at the American Museum of Natural History. If you go online to AMNH for American Museum of Natural History.org, you'll find the Virtual Universe program, part of the Hayden public programs.
And it might be worth saying, you got about 400 seats or so there that people can sit.
We have 429 seats and in our theater, and so the public comes in on these evenings, and unlike our movies, which are highly produced, and we really do the best job we can on those, that we can operate this atlas interactively. And what I mean is that we can move us as the planetarium, that we are the camera, if you will, and we can move out into the stars. Now, I had been doing sessions on Sunday nights, inviting friends in and so forth in the past, and this sort of led to this live program. But what we're looking at is what we call the digital universe, which is what we've done at the American Museum is take these three-dimensional data sets, this amalgam of data sets, and contextualize them by placing them one inside the other. And so you have a three-dimensional visualization of all these components put together contextually.
And you get the data sets from where? NASA or from where?
From various academically published sources. So for in academia, when you publish...
That wouldn't have been available 50 years ago.
Components or precursors to what's available now, because you're dealing with technological innovation now that has brought us up to a point with detector technology, and basically you have the technology of computing technology hooked up with the ability for imaging technology, which has revolutionized so many fields, but has revolutionized astronomy. And so the acquisition of data and the automation of the processes to actually to process that data.
Integrate them into a pattern.
We have, for instance, we have 118,000.
That can be visually displayed.
Yes. We have 118,000 stars. And brought to us by the European Space Agency's Hipparcos star catalog, named after the Greek astronomer who made the first star map, really, arguably, in antiquity. And then you have the zoo of objects that sort of make up the Milky Way, these different data sets that are co-registered and interspersed with one another so that you can show the layout of the galaxy. Then we have about we have about now plotted for galaxies beyond the Milky Way. We have on the order of about 1.5 million galaxies.
Holy
now this is very interesting.
Do you have some sort of a Cray computer or something, or how is that all integrated?
Modern graphics
Yeah.
cards in PCs. Basically, we have a PC cluster. It was donated to us by the NVIDIA Corporation.
A PC cluster. What is
We
that?
have
A number of PCs that are
we have a
connected?
number of PCs that are synchronized with one another.
Uh-huh.
And the reason that we have to do this to make up the resolution that is on the dome.
It's staggering.
We have 7 projectors. And 7 projectors, each projector has a computer behind it, and then we have to synchronize those together so that when we effectively translate through the data set, we see the stars moving past us, sort of like Star Trek fashion. Now, when I started to do these sessions on Sunday nights,
this is scientifically correct
everything
data.
is scientific data, so it is correct, and we curate. We curate these academic sources being brought into one. So while we do not generate these data sets, we are providing a common display of them, and that's what's unique about this.
And this place you display is on the dome.
Yes.
It's geodesic looking, at least from the outside, and it's the dome that is like you have a television set. There's a display screen.
We have a 68-foot
But you have a
dome.
display screen that is like a universe. It's huge, and it's the largest, or these planetariums would be the largest display screen, and it makes IMAX look like the Cineplex.
Well, IMAX also had an interesting development early on. In 1973, you had the Rubin Fleet Theater in San Diego, the first OmniMax, which was using the same projector
really,
as
I
IMAX,
haven't heard of that. Yeah.
But it was with a sort of fisheye lens to immerse you in the filmmaking. So there are various precursors to what we've done.
Well, that
but
usually is the case. But you're on the cutting edge.
Well,
now.
what's unique about our facility is to have this, to actually be actively curating, pulling together, and making this digital universe. Brian Abbott, my coworker, who works directly for Neil Tyson and under the Hayden auspices, actually curates the digital universe data set. Now you can download a free version of this. You can download our data and with a free viewer. And this is on something called haydenplanetarium.org website.
haydenplanetarium.org.
And when you go there, you'll see Digital Universe. And if you go to Digital Universe, you can then download the data set, and you can download the viewer, and you can go flying through the universe, not on a big dome, because we have the dome, but on your single laptop screen.
Number of things I wanted to talk about that. The Rose Center is the Rose Center for Earth in Space or something.
Absolutely, yes.
It is the Earth in Space. So because you also give renderings of the Earth, you gave us renderings of the Earth on this dome that was so massive and so beautiful and so and you can be presenting images that are earthbound.
Yes, and in
Parts
fact,
of the Earth,
and this is what I'd like to get to.
And things going back, and also one last thing, you had a couple fellows, if I may, a couple fellows who were there. We say they're from Sweden. They were involved. They said there's about 30 or 40 people on the cutting edge of this kind of visualization, so around the world, and that they're going to have a massive jump in terms of the resolution that's going to be possible, because I presume there are advances coming out of the computer labs that are making more and more available ability to render these images in startling new dimension and clarity.
Yes,
is that correct?
Yes. Well, let me explain
qualitatively new, perhaps.
Okay, let me explain
You're on the cutting edge of visualization for the human society.
I guess so. There are others that are colleagues in this field.
No, but I mean, you haven't got anything out of the movie industry or anything that gets into that kind of capability?
Occasionally, I mean, the movie industry will do pieces. Well, they will take on subjects where they want to visualize from data accurately what's happening.
Yeah.
But
you guys are on the cutting edge of that, and and the educational potential is absolutely staggering.
Well, yes, it is.
You can fit all kinds of databases into that.
So let me explain about the world and
how
we get to the Earth. Well, how we get back to the Earth is that the planetarium, the traditional planetarium, you sit as though you're in a field at night and you look up at the stars. But now, with this technology, we fly up into the stars, and we fly out, and we can fly out of the galaxy. What I feel that I've learned in this tenure of working on this material is that the only way to really view that contextually is to fly backwards. And so I have a little joke, which is that flying through the universe is the art of flying backwards, is that you fly out and you're constantly looking back. You watch the Earth shrink to become a point. Yeah. Then you watch our star disappear because it's so dim. Our star is a very dim star in the scheme of things, relatively speaking. It's, of course, the brightest thing in this for us because we're so close to it. But if you were to back off, the sun is actually a fairly dim star in the galaxy. And then when you leave the galaxy, we start to lose the Milky Way. It's just a little data point. And you're suddenly out in this field of like 1 million galaxies, and you're saying, well, where are we? It is a humbling experience.
Yes.
However, it's also an elevating experience because what we're showing is the resolution of this information at the current time, which has been brought to us by the entire lineage of humanity.
Thank you. 200,000 years. And we're reaching at a point where we're going to take the measure of it from 1 nanosecond from 13.7 billion years ago. The whole damn thing.
And it was only the year my father...
Something qualitative is going on, brother.
My father turned 84 this year. He was born in 1980. He was born in 1923. This was the year that Edwin Hubble was able to definitively show that the Andromeda Galaxy was, in fact, not something that was small and near, these sort of spiral shapes that astronomers had seen.
It is the nearest, isn't it?
It's one of the nearest large grand spirals like our Milky Way. We have smaller things like the Magellanic Clouds that are orbital to us. They're sort of companion galaxies to us.
Okay.
But the thing is that Hubble was able to show that the Andromeda was another thing the size of our Milky Way. And the Milky Way, to that point, it was a big debate actually in 1921 at the Smithsonian about whether the Milky Way was the entire universe or whether these little spiral shapes that we were seeing were actually other island universes like the Milky Way. And so Hubble in 1923 showed that Andromeda was another galaxy. And by the time of the end of the 20s, the time of the stock market crash, 1929, Hubble published a paper that distanced galaxies, other galaxies, and showed a property that others had found and had worked on, but Hubble put the picture together. And that was the farther these galaxies were away, their light, their characteristic barcode of the spectral signatures of emission lines and things like this, which you see in galaxies, were shifted farther and farther to the red, which meant that they were receding away from us. There was this general trend. Andromeda is actually approaching us because we're going to smack together and hit in a few billion years. Billions of years that we're looking at for that. So don't worry about that.
It's going to get that bad.
Around the time our sun, the star, actually starts to burn out, we expect to be colliding with Andromeda. But before that happens, basically, we're looking out into this universe. Hubble finds by 1929 that the universe seems to be expanding. It's as if our view is as if we're in the middle of some big explosion. But now think, if you translate yourself to one of those other galaxies, you would see the same effect. And so the universe seemed to be expanding. Well, that seemed kind of crazy, but he published this. And what made Albert Einstein a household word was that in 1912...
special theory of relativity or general theory?
General theory of relativity, as published in 1912, predicted that the universe would be either expanding or contracting, but can't just be standing still. And in fact, no one saw evidence of an expanding universe at that time with that resolve of the data. And so Einstein had to put in what was called the cosmological constant to sort of fudge factor, if you will, to sort of account for this. And so out of this, Hubble finds the universe to be expanding. This vindicates Einstein. But what it also set up, and Fred Hoyle called derisively, this beginning of the universe. So the universe is expanding. From when did the universe expand? And so you can run the expansion rate back and you say, well, the universe must have, in that case, been a super dense hot plasma or just
atomic size or something.
Or, just born out of this sort of singularity event. And Fred Hoyle derisively called it oh, now you're saying the universe was born in a Big Bang, and so
and it was sort of like a joke or a derision.
Sort of a derision. But and so others came up with the notion that the universe perhaps has this steady state to it, that it's expanding, but somehow magically in the cocktail of energy and matter, that matter comes into existence and then goes out of existence.
Hoyle had that or no?
Well, Hoyle and others were trying to come up with an alternative to this notion that the universe had an opening act.
They're coming up with string theory now. Brian Greene and that, and Kokaku, and they think that there may be parallel universes connected by wormholes.
There may very well be.
And that may be an escape clause to get to another universe when this one runs.
But to anchor this back to that which we see, what was predicted out of this expansion was that there might be an echo, that the proof of the Big Bang, the smoking gun, would be that the universe has some sort of echo in it, and that this is
a shock wave.
Basically, you take the fact that we can see through space clearly, and that if you take the flash of the Big Bang and you cool the universe down to basically from where it is a plasma, and that's opaque. Actually, you don't see into the sun. You see the surface of the sun. That photosphere is that the universe would have expanded and cooled, and at a certain point, about half a million years after the Big Bang itself, the universe goes from being opaque plasma to being clear space. And that if you calculate what we could see of that now, that the universe would seem to have a temperature of about 3 degrees above absolute zero. And at the time that this was predicted, around the time the atomic bomb was being created and all this, or the musings around that we had no way to detect that. But Arno Penzias and Robert Wilson found this at Bell Labs, actually, in 1964, I believe, and then they got the Nobel Prize for this. But and a Princeton professor, Dave Wilkinson.
That's after the telescope's named after him.
Yes, and because he was actually building an instrument to actually do this measurement.
He gave us a telescope where you get it with about 200,000 years after the Big Bang.
That's right.
That's what we have currently. We've got pictures of that.
So that's
pretty amazing.
And the picture that we get is an all sky, we call it. It's a picture of the entire sky. And there's a very, very slight, they're exaggerated by about 100,000 or so, these slight temperature variations to it. And that these slight temperature variations are going to what leads to the concentration of mass here and there, which that will later form into these superclusters of galaxies and things. So we show that. That is sort of the edge. It's the edge of our view. It's not the edge of the universe. It's a horizon. It's a limit of our view in space and time. Because you have to imagine that as we look out at the stars, we are seeing the closest stars the closest star to us 4.5 light years away. The sun is 8.5 minutes away.
That's
the
not
moon,
Andromeda.
The moon is a second and a half.
Go ahead, go
And
ahead.
so then the stars that we see, we're seeing basically history. When you look up at the stars, you're seeing stars that, are some of those stars that you're looking at may be
burned out.
Light. Maybe not burnt out yet because of the life cycles of them or durations, but we are seeing a history map. When you look at the star Deneb as part of the summer triangle in the night sky that's now rising into view and that we see more and more above us as we go into summer, is that star is 2,000 light years away, roughly. And we have great uncertainty for that as you go farther out for that distance measure, but it's a bright star very far away. Next to it is another bright star, which is nowhere near as bright as that star. It's 2,000. The star Vega, and Vega is only 26 light years away. But so it's close to us. So and we're able to plot all this and fly through
data sets,
Right. And but the issue is that you are looking deeper and deeper, you're getting that information older and older. So if you look far enough out, you're actually seeing that point where the universe went from the sort of being opaque to being clear. And because we're expanding, that also represents where we were a lot smaller.
Taking the measure of the whole damn
the whole
thing.
But
you couldn't think about doing that 20 years ago, 50, I mean, everything's coming
We
to
had the concepts then, but we didn't have the data. And so now what we're doing, and we didn't have the technology to,
it's all coming in Niagara proportions right now. Every day over the transom comes a revolution. And we're taking a measure of the material or the world in new kinds of capability that are staggering. And the educational possibilities are just absolutely staggering.
So we fly out there to the edge of the universe, and then you come back. You say, where's the Milky Way? There it is. I see the Milky Way. Come up on it. You get into the Milky Way, you say, all these stars, where's the sun? Oh, there it is. And we mark it. We come close to the sun.
Where's the Earth?
And you say, where's the Earth? The big thing that's new, in a way, in planetariums is that now we come up, just as the Apollo astronauts came back from the moon, we come back to the most colorful, most beautiful planet in the solar system.
And as far as we know, the only place where there's life.
The most diverse, balancing on this thin edge of habitability zone.
It's staggering. It's impossible that where anything exists.
Well, it's a habitability zone that we talk about around stars, which is where you can have liquid water. And liquid water to us is life. That's the life that we know of.
There may be other forms, but...
But life is that lowest common denominator for life here on Earth. And so liquid water, and you have to have liquid water. On Venus, it's too hot. And on Mars, it's too cold. Although there may be places where we know that Mars was warmer in the past. There's ice on Mars, and there may be liquid water trapped.
We don't have any examples of intelligent life yet that we've tried to get, Arecibo and so forth.
But you come back to this planet with its very thin atmosphere. If you take the island of Manhattan and tip it on Bowling Green straight up, that is the height of the atmosphere. It's only about 20 miles thick. And
then the parameters where anything could happen like it has happened is absolutely staggeringly against that anything exists on this planet is, much less us, is absolutely the odds against that. Nick the Greek would have thrown up his hand at ever taking the odds on that possibility happening.
It's very interesting.
Because
we are
it's
now
just in such a narrow little plot that it had to be just so much, and everything had to be just right.
It's got this incredible diversity, this incredible mix in the natural world that we see. These forms that just you couldn't imagine. These forms is just sort of, and then you see in these deep ocean vents where there's no sunlight, you have life down there.
Sulfur-based things, life that aren't even photosynthesis.
There may be smokers on the moon of Jupiter called Europa, we know that there's liquid water below an icy crust. So the thing is this. Is that we come sailing back to Earth, and suddenly you have Earth, and you want to see Earth. You want to see it as the astronauts see it. You want to see the thinness of the atmosphere.
Well, okay,
we were limited.
But you want to get down to the Earth itself, too, and the wonder of the Earth displayed within these visual display arrays that you have.
Well, when you get back to the Earth, you are then in a realm.
I mean,
the Earth. You can exit the planetarium, and then you have the entire museum curated by all the various scientists. We're a research institution, so that we have paleontologists in the field. Out in the field, we have mammalogists, we have ichthyologists, we have all these research scientists out there, and the result,
incredibly interesting stories.
Exactly, and the panoply of all this is the Museum of Natural History.
Now you can present these things from the beginning of the Big Bang right down to all kinds of natural history events in the universe, and present them on this array, this screen, in a way. And did you not tell me? I don't know. Maybe it's out of that it's coming from and it's all a matter of computer technology. We're now talking about terabyte computers, home computers at a terabyte level. We're talking about beyond Moore's law, just galloping beyond Moore's law. We have the capability of presenting these things, and the educational content. That is just an absolutely staggering thing. You could have things put on there. And there are possibilities that you're right on the leading edge.
Let me describe.
And how far can we go with that in terms of getting it to the people of the world as a way of presenting data in a multimedia, sensorially exciting kind of way that's going to be revolutionary?
Let me describe that our dome working with the data interactively when we move through it, as I say, with mouse, we do these presentations. Online gaming has enabled the ability to coordinate or be able to be in any place in the world and be there are things like Second Life where you maneuver through this world, but you see other people, avatars, that are moving through the world as well. It's like a city that doesn't really exist. It's in cyberspace. So
virtual reality.
Yes. And so we are about to, with this software, be able to link our dome with other domes. The Denver Museum of Nature and Science, which in many ways is sort of a sister sister museum to ours, a very similar natural history museum.
There must be a camaraderie among you domite
absolutely,
dwellers
and we're collaborating
the
with them.
Yeah,
they collaborated with us on the last space show, and we are collaborating in the development of this software now that will enable us to talk and have a common program dome to dome. Let me describe to you.
Dome to dome.
Dome to dome. Let me
ask you something.
Well, no, let me describe that.
We've only got 5 minutes, 4 minutes left.
Okay, let me describe that.
Get it all in, Ray.
We had Kevin.
Get the whole universe in.
We had Kevin Grazier who's an engineer, flight engineer and scientist on the Cassini mission for Saturn. He came in and gave a wonderful presentation as we could follow the spacecraft around Saturn, visualize this on the dome. But once the lights go out, you hear Kevin talking. And he's pointing things out. He might as well be in Kalamazoo. And so if he was in Kalamazoo and had the software bridge, essentially, say he's looking at his laptop screen, but we are seeing the results and hearing him.
On the dome?
But we're hearing his voice, but we're actually seeing him control the visuals. Is that networked presentations between sites and most importantly, between classrooms, so that classrooms will be able to follow, say, a lecture that's given in the planetarium. That's where we're going.
Fantastic. With this. And the visual presentations that can be there, I mean, it's like staggering and so on. There's so much. Well, I want to apologize again. We couldn't because of ourselves. We couldn't get your display. We could have been display some of these.
Well, I'll have to come back.
Next time we'll come back. Maybe it'll be at a level of capability that is emerging, capability to render beautiful graphics and so forth. We do that. Could they ever get it down? Because I'm sitting there looking at the thing. This is one last question. I'm looking. Couldn't they have something that would go on somebody's head? Like a dome.
There have been various ideas for that.
And that it's surround sound, and it's a go, and you got surround sound, and because when you're sitting here looking at a dome, you're looking at an image. Could that be brought down into something that could be individualized off a PC in somebody's living room?
Yes, there are various things called hoods that you can wear and devices for that.
And is that coming? And is that in competition?
No, it's not.
With the planetarium.
Let me describe why it's not. The planetarium.
Because it's all a database. It could be set out around the world.
Yes, the data could be seen by you sitting in a closet with your laptop,
or anybody who wants to get educated,
or the closet-sized apartments in New York.
Yeah, right.
But my point is that the planetarium is a theater.
Yeah.
It is a group experience.
It's something beyond. It's beyond theater.
Where you go and you have a special evening where you walk in, or a special presentation where a person of authority who has talked about this, moderated by curators who are there, and so forth.
Yeah, but
that you have an experience that is a theater experience. It's a group experience, and I think that's actually a really great thing, because it's a small little community there that you then go on a journey together, and so you can all talk about it with one another and so forth.
Yeah, that is good. I agree with you with that. There's like a symposium or a seminar or something like that.
It's a community group experience.
Yeah, but that other thing is something that could come because you could have the authority of the good science and the good presentation built into the program.
I should mention that one company that we're
there'll be competition in the market coming out with that stuff.
There's a company called Illuminati.
Yeah,
and they make inflatable domes.
We're going to have to run the graphics, I think, now.
They make a dome that you can inflate the walls of. You walk in, it's like an igloo.
Thank you,
inside,
Bucky Fuller. Yeah.
Yes, and so you then project with a fisheye lens this map. And I've done this. We actually took this technology out to Burning Man, the arts festival in the desert. And it was the #1 attraction of Burning Man, this traversal through the universe, coming and going to Earth. And so you see the context of us in space and Earth. And we didn't get a chance to talk about the Swedes, but this involvement with Linköping University, they're sort of Swedish MIT over there.
Yeah, they were there.
And these are my students, interns, a series of them, who have developed the software that we're now running. And that's called UniView. It's for Universe Viewer.
Yeah.
And it can traverse all the scales. You're not limited to what computers usually have a floating point. It's a realm of numbers to deal with.
Right.
You get out of that box, and now that range of scales allows you to go from the subatomic or string theory of these tiny, tiny dimensions all the way up to the largest conception of the universe that we can see.
I know.
And putting that together into one picture, and universe means one verse, means one intonation for the all. And so what we're trying to create is a viewer to the intonation or the view
of the
all
the
in
noosphere.
one.
I mean,
that's right.
Teilhard de Chardin spoke about the